Hi, hello. This video is a continuation of our power amplifier discussion. Okay, so on our part 1, we have discussed Class A, both for the direct coupled and the transformer coupled Class A amplifiers. So for this video, we will be discussing Class B, Class AB, and Class C amplifiers. Okay, so to start with, we know that in order for us to say that it is Class B amplifier, we will be designing the circuit in such a way that its Q point lies directly across the cut-off region. Okay, so when we place our Q point here, okay, so it is said that and place an input signal in this manner. Only during the positive half of your input signal you have an output signal. Okay, so the output signal only occurs during the positive half of your input signal. So this is the current transfer characteristic and this is your output characteristic. Thus, we say that Class B amplifiers operates only at 180 degrees of its input cycle. Okay, so these are the characteristics of our Class B amplifiers. So since negative half cycles are totally absent from the output, the signal distortion is high as compared to Class A amplifiers. So our output, if we're going to look at this, is like a half-wave rectified signal, no output during the negative half cycle. So comparing your input, this is your input and your output signal, they do not look alike together. So when the output doesn't look like your input signal, there is definitely distortion. So we call that distorted signal. Unlike Class A, your output signal looks exactly like your input signal. Okay, so now second characteristic, since input voltage is large up to VCC, since we make use of the cutoff region, voltage amplification is reduced. Okay, because your input is already high, so therefore your voltage amplification is likewise reduced. Okay, so zero signal input represents worst case condition for Class A amplifiers, but it is the best condition for Class B amplifiers, because when your input signal is zero, you don't have going back here, when our input signal is zero, we don't have a DC current. Okay, so our current here is equal to zero at zero input condition. So therefore, at zero signal condition, your transistor is not dissipating any power. Okay, so for Class A, it is the worst condition, but for Class B, it is the best condition because the transistor itself is not dissipating power during this instance. In Class B amplifiers, transistor dissipates more power with increase in signal strength, okay, but opposite in the case of Class A amplifiers. So average current in Class B operation is less than in Class A. Hence, power dissipated is less. Okay? So consequently, the maximum circuit or overall efficiency of a Class B amplifier is said to be 78.5% when peak signal makes VCE mean equal to 0. So in general, the overall maximum gain is 78.5%. So this is much higher than compared with Class A amplifier, because for Class A, its maximum theoretical is just 50% if we are using a transformer coupled, and it is just 25% when we are using direct coupled. Okay, so the half sine wave type of collector current contains very pronounced even harmonics, particularly the second one. These impulses can be rendered useful either by employing push-pull circuit or by using tuned amplifiers. So we will be discussing tuned amplifiers and push-pull circuit on our next slides. Okay, So these are the power relations for class B operation. So input DC power, okay? So input DC power is equivalent to VCC times IDC. Okay, so your IDC here is not your ICQ, because if you're going to look back here at the 0 point here, at 0 input condition, our IC is equal to 0. So we cannot use that because we cannot because that will always give us an answer which is equal to 0. But instead, since we still need a DC current, we will be using DC, or the average, or the DC current drawn from the supply. So from your AC source, okay, what will be the DC current out of that AC current? Okay, so we call that DC as the average, or the DC current drawn from the supply. And your IDC is equivalent to IC maximum divided by pi. Okay, so if we're going to make use of this 1 all over pi, this will give you 0.318. So that if you can still remember that 0.318, that is the value when you have to solve for the DC current, okay, for a half-wave rectifier circuit. So it will be the same IDC that we're going to make use, because if you're going to look at this technically, we have a half-wave rectified signal. Okay, so where IC max is the maximum or peak value again. So peak value is different from the peak to peak or from the RMS value. So what we are talking about here is the peak value of your collector or your output collector. Okay, so your P in DC now is equivalent to VCC multiplied by your IC maximum divided by pi. Okay, so this is your maximum current when you have your input, but we have to divide it by pi to get your average DC current. So the DC power loss in the load is your PRDC, still in DC. So we have your IDC squared multiplied by RC. And the AC power, or developed across the load, so this is what we wanted, from your DC to be to convert it into AC. So your POAC is equivalent to I squared RC, V squared RC if these are RMS values. But if we are using peak values or maximum values, so this is equivalent to VM squared all over 2RC. So the DC power loss in the collector region of the transistor is given by PCDC, which is just the difference from the input DC current from your PRC DC and POAC. So whatever is left here, that will be your DC power that is lost in the collector region of the transistor. So that is the power that was dissipated by your transistor. Now, the overall gain is still the same. It is POAC divided by P in DC. Okay? So, for maximum values, your IDC here, so when we say maximum, we're going to make use of the saturation and the cutoff region. So this is your Q point. So therefore, we have an input voltage which is equivalent to your VCC. So VCE is equivalent to your VCC. So your ID is equivalent to IC max. So IDC is equivalent to IC max all over pi. Okay. So IRMS is equivalent to IC max over square root of 2. VRMS is VCC over square root of 2. Okay, so converting them to RMS value. So peak value divided by square root of 2. So VCC is your peak value. So P in DC is VCC times IDC, wherein IDC is IC max all over pi. Okay, so POAC now is IRMS times VRMS. So that is IC max divided by square root of 2 multiplied by the VCC divided by square root of 2, giving us 1/4 VCC multiplied by IC max. Okay? So, we have here POAC. So we have here your POAC, which is equivalent to 1/4 of your VCC multiplied by IC max, and P in DC all over VCC, IC max all over 2. Okay, so we have here 1/4 VCC IC max all over. So it will be cancelled out, giving us pi over 4, which is equivalent to 78.5%. Okay, class. So this is the maximum theoretical efficiency for a Class B amplifier. Okay? So we have to remember that. So what do we expect? So we can expect a value which is lower than 78.5 because 78.5 is already the maximum value, and this is theoretical. So this is for discussion purposes only. Now, if you can see, so if you might be saying, our output is half wave since your input is a pure sinusoidal waveform and our output is sine wave. So Class B amplifiers is really prone to distortion, or the output waveform is really distorted. Okay, so what do we do since the output waveform is distorted? We actually use okay, two Class B amplifiers. Okay, so in this manner, they are connected in this type of manner. So this is a Class B amplifier and this is also a Class B amplifier. Both of their Q points will be located at the cutoff region. So we call this connection as Class B push-pull amplifier. So what do we mean by a Class B push-pull amplifier? So each of these transistors here will have an output waveform, okay, in a form of a half wave. So if this is our input signal, look at this one. We have an input signal here. So we have a center tap transformer here. So at both instances, okay, so this will have a positive half and this will have a negative half. During positive half cycle, so this transistor here will be turned on. Since this is common emitter configuration, a positive half cycle here will result in a negative half cycle here. For this configuration, so this will be turned on during the negative half cycle, and a negative half cycle here will result in a positive half cycle here. Considering this both, okay, or combining this both, we can have an output just like this one. So as you can see, we do not have, or we do no longer have a distorted output. Why? Because these two works together in the form of a push-pull amplifier. Okay, so this is usually the circuit for a Class B amplifier. So, a Class B push-pull amplifier, also known as a balanced amplifier, is when when we use two identical transistors operating as a single stage amplifier. Again, why didn't we discuss this in compound configuration? Okay, so this is not included in the compound configuration because technically, although we make use of two transistor circuits, they do not operate single stage. So usually the two of them work together to form a single stage amplifier, unlike the conditions in compound configuration. So in configurations, they can function separately, but in this case they operate as one. Okay, so the two transistors must be identical for us to have a balanced amplifier circuit. So the base of the two common emitter configurations are connected to the opposite ends of the secondary of the input transformer T1 and the collectors to the opposite ends of the output transformer T2. Okay, so we call this a balanced circuit because the two emitters have been returned to the center tap of T1 secondary and VCC connected to the center tap of the primary T2. Okay, so however, we have here the output of a Class B push-pull amplifier. So as you can see, there is a portion here wherein we have somewhat a distortion. Okay, so there is a portion we call this as a crossover distortion. So what is this crossover distortion and how does this happen? Okay, before we discuss that, let us first discuss the advantages for a class B amplifier. So number one, it has high efficiency, theoretical limit being 78.5%. It is primary due to the fact that there is no power drawn by the circuit under zero signal condition. So therefore, under zero signal condition, no power is being wasted. So it added to the efficiency, or it added to the output AC power. So since push-pull arrangement, 180 degrees phase difference exists between even order harmonics produced by each transistor, they cancel out. So the even order harmonics, which is considered as unwanted signal, they tend to cancel out, thereby giving an almost distortion-free output. Okay, so this automatic cancellation of all even order harmonics from the output makes Class B push-pull amplifiers highly desirable for communication signal equipment. So usually we can see Class B amplifiers in circuits in communications. Okay, so this double-ended Class B amplifier provides practically 4 times the power supplied by a single-ended amplifier, provided signal load resistance remains the same. Okay, so the DC components of the two collector currents through the two halves of the primary of T2 flow in opposite directions so that the net DC magnetization of the transformer core is almost nil. Hence, distortion due to the effect of DC magnetic saturation of the transformer core are eliminated. Moreover, a smaller size core can be used to very small net core flux. Okay, so what are the applications for Class B amplifiers? So this is usually used in audio work, in portable record players, so for stereo amplifiers, and for high fidelity radio receivers. Okay, so we have here the figure of a distortion somewhere located in this part of your output signal. Okay, so that distortion is what we call the crossover distortion. So what is a crossover distortion? So this is a severe distortion at a very low signal due to, okay? So due to two things. So we have here the bases of the transistors. So we know that either you're using a silicon or a germanium, your transistor is really not turned on unless it reaches a voltage of 0.3 or 0.7 for silicon or germanium transistors respectively. Okay, and also there is non-linearity in the low signal area of your transistor operating region. Okay, so this crossover distortion occurs during the time the operation crosses over from one transistor to the other in a push-pull amplifier. So in a push-pull amplifier, when your transistor is when the first transistor is in the on state, the second transistor must be in the off state. And when the second transistor is in the on state, that means the first transistor is in the off state. But there is this time that the first transistor is already off and your second transistor is not yet turning on. So that is the moment when your crossover distortion occurs. Okay, so we have what we call the dead zone. Okay, so the dead zone is neither transistor is turned on. So ideally, when one is on, the other is off, and when the other is off, the other one is on. So that is the concept of push-pull. But that is the ideal situation. But in we have the dead zone wherein there is a time that both transistors are still not yet turned on. They are both off. Okay, so we call that the dead zone when neither transistor is turned on and the output is equal to 0. So that area is usually equivalent to 1.4 voltage. Okay, so to illustrate that, this is the moment when your output of your first transistor, and this is the output of your second transistor. Okay, so this is what we call the dead zone, when neither of them is still turned on. Okay, so usually it is equivalent to 0.7. This is 0.7 and this is 0.7. If we get the total for that, for a silicon transistor, it will be equivalent to 1.4 volts. So that is the crossover distortion, or your dead zone. Okay, so to eliminate that problem, okay, actually this is a distortion, so therefore we have to do something about that. We have placed a small bias voltage, okay, a small input voltage. We raise your Q point just above, okay, your cut-off region. So as you can see, that for a class A amplifier, your Q point must be located at the center. For class B, it is located at the cutoff. So we place our Q point somewhere between class A and class B, so that during the time that both transistor is turned off, okay, there will be a small input bias voltage, so that we can remove the effect of the crossover distortion. So in that case, if that happens, we no longer have the crossover distortion here. And since the Q point is literally placed between the center and the cutoff region, we call this configuration, or we call this biasing, as class AB, because we place the Q point between the center, which is class A, and the cutoff, which is class B. So therefore, class B is somewhat lower than 78.5%, but it removed the effect, or it removed the problem of the crossover distortion. Okay. We also have here another circuit, and we call this as the complementary symmetry push-pull class B amplifier. Why? So what's the problem with the previous balance amplifier? So the previous amplifier circuit requires a bulky and expensive output transformer. Okay, so we have it requires two out-of-phase input signals. So since it requires two out-of-phase input signals, we make use of the output. We make use of the center tap transformer. So which necessitates an input center tap transformer or phase inverter, and thus it makes the driver circuitry quite complicated. Okay, so to eliminate those. So to eliminate those now, we just make use of the complementary symmetry push-pull class B amplifier. So this is our circuit for a complementary symmetry push-pull amplifier. Take note that we have eliminated the use of your center tap transformers. What we do is that we make use of a complementary transistors. So what do we mean by complementary transistors? We make use of NPN and PNP transistor. So we only need one input signal, okay? So because your NPN and your PNP works differently, in such a way that NPN works with the positive half and your PNP works during the negative half cycle. So therefore, we do not need to make this input half, okay, or out of phase, because during the positive half, your NPN will be turned on, and during the negative half, your PNP transistor will be turned off. Okay, will be turned on rather. So therefore, this eliminates the use of a transformer, and yet the concept of push-pull is still within this circuit. Okay, why? Because when the PNP is working, the PNP is not working. And vice versa, when the PNP is working during the negative half cycle, it is the NPN which is already in the off state. Okay, so when can we say that they are complementary and symmetrical? So there are two transistors that really are complementary and symmetrical. So in our laboratory subject, the 3N0904, which is an NPN transistor, and a 3N0904 and 3N0906. So the 0906 is the PNP transistor. So they are complementary because one is NPN and one is PNP, and yet they are symmetrical because all of their parameters, all of their characteristics are the same. They share the same beta, they share the same gain, they share the same temperature coefficients, and so on. Okay, so the only difference between the two is that one is NPN and the other is PNP. So that is when you say complementary and symmetrical. Okay, so our example there is the 3N0904 and the 3N0906. Although, if we're going to make use of power amplifier circuits having a higher value of currents, we cannot use those two because those two are small signal amplifiers. So there are also power transistors, okay, so NPN and PNP power transistors that are complementary with each other. Okay, so let us discuss some of the sample problems regarding Class B amplifiers. Okay, so we have here, for the circuit shown, calculate the input power, the output power, and the power handled by each output transistor and the circuit efficiency for an input of 12 VRMS. Okay, so listen, so in this case, we didn't use the balanced amplifier because we don't have any transformers here, but we use two complementary transistors here, one NPN and one PNP transistor. Okay, but before we go to that, I would just like to discuss to you some important things. Okay, so I would just like to discuss to you some important things regarding our formulas. So we have here some other books, some other references, they make use of IC maximum, some other references, they make use of IP for peak. Okay, so some other books they use max, or some other books they make use of peak. So we have here your PNDC is given by VCC all over 2 over pi multiplied by IP. Now, why 2? Because we now make use of two Class B amplifiers. Okay, so because if we just make use of only one Class B amplifier, we will have our input is different from our output because our output will just be a halfway rectified circuit. So to get the full input, we will be using two circuits in a push-pull manner. Okay, so therefore, we have here 2 IP divided by pi. Okay? So your POAC here is equivalent to VL. So that is the voltage that was transferred across your load, okay, in RMS, divided by RL. So if we're going to make use of peak to peak, so that will become the load voltage peak to peak squared divided by 8 RL. And if that is in terms of peak voltage, that is equivalent to VL peak squared divided by 2 RL. Okay? So the larger the RMS or peak output voltage, the larger the power that is delivered to the load, of course. It is directly proportional. Okay? So as we said earlier, the larger that was the larger voltage that is being transferred to the load, the highest efficiency, the higher the efficiency. Okay, now, for the maximum efficiency, that only means that all of the power that all of your VCC was all transferred to your load. So this is the condition for the maximum efficiency. So maximum efficiency means that all of your VCC was transferred to the load. So the power dissipated by the output transistors is equivalent to P2Q. So why 2Q? Because technically for a push-pull amplifier, we use two transistors. So there are two transistors that also dissipates power. So that is equivalent to your P in DC minus your POAC. Okay? So let us say symmetrical. So they will be receiving the same amount of power. So that will be equivalent to P2Q divided by 2, assuming that we are using complementary symmetrical transistors. Okay, so considering maximum power considerations, we have here POAC maximum is equal to VCC. So that is our maximum considerations when all of your VCC will be transferred to your load. So that will be VCC squared divided by 2RL. Then your peak current now, okay, is equivalent to VCC divided by RL. So the maximum IDC is 2 VCC all over RL times 2 all over pi. So your maximum IDC now is equivalent to 2 over pi. Maximum IDC is VCC multiplied by ID max. But what is ID max? ID max is 2 pi VCC all over RL. So multiplying this 2 will give you 2 VCC squared all over pi RL. Okay? So efficiency is P in P out all over P in. Okay? So canceling your VCC, canceling your RL, considering maximum power transfer, so your RL is the same. So divided by, so canceling your 2 there, 2 times 2 here, that will give you pi over 4. So even for a push-pull or a single class B amplifier, the maximum efficiency class is 78.5%. Okay? And this is achievable if your power delivered to the load is equivalent to your VCC. Okay, so let us try solving the problem now. So our problem is, for the circuit shown, calculate the input power, output power, and the power handled by each output transistor and the circuit efficiency for an input of 12 VRMS. Remember that our input is RMS. What we have in our discussions are peak voltages. Okay, so what do we do is that we convert first your RMS voltage into peak voltage. So your peak voltage, input peak voltage, is equivalent to square root of 2 multiplied by your VIRMS. So square root of 2 multiplied by 12, that will give you 16.97 volts, approximately equivalent to 17 volts. Now, your amplifier has ideally have a unity gain. Okay, so how did we know that we have a unity gain? Consider the circuit class. Okay, so look at the circuit. Where is your output being taken? Your output is being taken at the, what is this? This is the emitter terminal, right? So the emitter terminal, when your output is at the emitter and your input is in your base, we have what we call a common emitter configuration or an emitter follower configuration. And we know that for a common emitter, for a common collector configuration or an emitter follower configuration, your voltage gain can be no greater than 1. So ideally, its value is equivalent to 1 or it doesn't amplify. So this circuit here, since we get your output here at the emitter, so this is an emitter follower configuration. Therefore, we have here the amplifier. Okay, the amplifier has ideally have a unity gain. Okay, so therefore, if our input is 17 and we don't have any gain, so the output is likewise equivalent to the input, which is 17 volts also. Okay, so the output power developed across the load now is equivalent to POAC, which is VLP squared all over 2RL. Because why we have 2RL? Because we make use of the peak voltage. Okay? So we have here 17 squared divided by 2 times 4 ohms. We have 36.125 watts. So the peak load current is the current across the load, which is VL divided by RL. So VL is 17 divided by RL, which is equivalent to 4 ohms. That will give us 4.25 amperes. Okay, so we need that IL so that we can solve for IDC. IDC is 2 times IL peak divided by pi. So that will give you 2.71 amperes. Okay, take note class that we have here a value of current in the ampere range. Okay, so why ampere range? So because we are now dealing with high power amplifiers. Okay, so usually the transistors that we are going to use in this type of circuits are what we call the power transistors. Okay, so going back here, we now know your P in IDC. We can solve your P in DC. So this is VCC times your IDC, and that is equivalent to 67.75 watts. So therefore, if we have 67.75 watts and 36.125 was developed across the load as your AC power, therefore, the power that was dissipated by the two transistors is equal to P in DC minus POAC divided by 2. So if we didn't divide this by 2, so this is just the power dissipated by the two transistors. But if we wanted to determine the power that is dissipated by each transistor, and assuming that they are symmetrical, we are just going to divide this by 2. Okay, so this is 67.75 minus 36.125 divided by 2. So that will give us 15.8 watts. Okay, so for the efficiency, POAC divided by P in DC, so 36.125 divided by 67.75 times 100, that will give us 53.32%. Okay, so 53.32%, is this acceptable? Yes, because the maximum allowed is, what is the maximum allowed? 78.5. Okay, so for we cannot do this in class A, because in class A, even though we use transformer coupled, the maximum is 50, and that 50 is theoretical, so it can never have an efficiency which is equivalent to 53.32, which is this 53.32 is possible for a class B amplifier. Okay. Okay, so let's have another example. So in this example, it says that calculate the maximum input power, maximum output power, the input voltage for maximum power operation, and the power dissipated by the output transistors at this voltage. So we are asked the maximum values. Okay, so what do we do if we are being asked of the maximum values? So for maximum values, okay, so we have here for maximum values, P in DC is equivalent to VCC. Okay, so we, instead of using the load voltage here, okay, we are going to make use of your input voltage, which is your VCC. So in case with our problem, it's not the 17 volts, okay, it's not the peak value, but it's the VCC. So, to consider the maximum input voltage. So, therefore, it is 25 divided by pi multiplied by RL, which is 4. So, the maximum input DC here is 99.47 watts. Now, what is your POAC max? So, POAC occurs, okay, when all of your VCC is reflected in your load. So, therefore, instead of VL here, instead of peak load voltage here, we will be using 25 as your VCC. So, that is equivalent to 78.125 watts. Okay, so if we get now the efficiency, it is POAC divided by P in DC. This is 78.125 watts divided by 99.47 times 100. And we get 78.54. So, do we expect this answer? So, yes. Why? Because we make use of the maximum value. So, if we use the maximum value, of course, we can have the maximum theoretical efficiency of 78.54 watts. Now, for the question of what voltage are we going to make use for this maximum power operation, of course, we are going to make use of the peak load voltage, which is equal to your VCC, which is equal to 25 volts. Okay? And for this case, what is the power that is being dissipated by your transistors? So, this is P2Q, which is your input power minus your output AC power, which is equivalent to 21. Okay? So, for each. Since maximum of the power is delivered to the load, so each transistor can dissipate only a few power or a small power. So, if you still divide this by 2, around 10 point something, okay, so that is just the power dissipated by each transistor during maximum power condition. Why? Because majority of the power was transferred to the load. Okay? So, we have here another example. Determine the maximum power dissipated at the output transistors. Okay. Determine the maximum power dissipated by the output transistors. So, a while ago, okay, so from the previous example, that is the maximum power across the load. So, this time, the question is the maximum power dissipated by the output transistors and the input voltage at which it occurs. So, for Class A amplifiers, the maximum power dissipation occurs when your input voltage is equal to 0. So, what happens, okay, for Class B amplifier? So, for Class B amplifier or Class B operation, okay, always remember this, that the maximum power dissipated by the output transistors does not occur, okay, at the maximum power input or output condition. Okay, however, it occurs, okay, so when your load or peak voltage is at 0.636 of your VCC. So, what is 0.636 of your VCC? If you're going to remember this, since you are operating full wave, so you have two transistors operating push-pull with each other. So, this is equivalent to 2 VCC divided by pi. So, 0.636, if you can still remember, this is the DC current, okay, or this is the DC voltage that was developed in full wave rectifier circuit. Okay? So, for maximum P2Q now, or transistor power dissipated by the transistor, we will be making use of this load voltage. So, this is equivalent to 2 VCC squared divided by pi squared RL. So, instead of VCC, the voltage that we're going to make use is 2 VCC all over pi. Okay? So, that will give us the maximum power dissipated by the transistor be equal to 2 VCC squared divided by pi squared RL. So, in this case, transferring or substituting that to our formula, we have here 2 times 25 squared divided by pi squared times 4 that is equivalent to 31.66 watts. So this is higher compared to, of course, this is higher compared to the maximum voltage, which is just 21.345 watts. Okay, and when will this occur? So this occurs at 0.636 of your VCC, or 0.636 of your 25 volts, and that is every time your input is equivalent to 15.9 volts. So when your input is 15.9 volts, your transistor is dissipating the highest power. Okay, so those are the different types of problems that you can encounter for Class B operations. Okay, any Class B, Class AB, or Class A operations, it is usually for about the power input, power output, efficiency, or the power dissipated by the transistor. Of course, you need to know the power being dissipated by the transistor, because you have to make sure that the transistor is still operating on the amount of power that it is still capable of handling. Okay? So we have here the next, which is Class C amplifier. In such amplifiers, the active device is biased much beyond cutoff. Hence, the output current flows only during a part of the positive half cycle of the input signal. So there is no output current flow during any part of the negative half cycle of the input signal, and your output signal has hardly any resemblance with the input signal. Why? Because your output here only consists of short pulses only. So remember, your input is a sinusoidal waveform, and your output consists of only short pulses. So therefore, it is very, very distorted. Okay? So, Class C amplifiers, but Class C amplifiers have the highest circuit efficiency of about 85 to 90%. Okay, so we can see here that the efficiency has nothing to do with the distortion of your output waveform. Okay, as you can see, the Class A amplifier has the one which is the one which has no distortion, yet it is the one with the lowest efficiency. Okay? So, because of high distortion, Class C amplifiers are not used for audio frequency work. Okay, so they are used for high power output at radio frequencies. So we can always see Class C amplifiers for RF amplifier circuits. Okay, so they are usually used in AM communication system, so in transmitters or AM receivers, where harmonic distortion can be removed by simple circuits. Okay, so they are used as high frequency power switches in radio transmitters rather than as amplifiers. Okay, so Class C operation, the collector current flows for less than half a cycle. Okay, so usually we see this in parallel resonance circuit. This can filter the pulses of your collector current and produce a pure sine wave of output voltage. So Class C operations are usually used for tuned RF amplifiers. Okay, so tuned, this is the combination of your capacitor and your inductor. Okay, so maximum efficiency can be 100%, although this is theoretical, but we can have a high efficiency of 80% and above. So this is a tuned RF amplifier. Okay, so resonant frequency, that is 1 all over, the resonance frequency is 1 all over 2 pi squared of LC. This is always intended to amplify a narrow band of frequencies. So this is ideal for amplifying radio and television signals. So they are usually being made use in radio or television transmitters and receiver circuits. Okay, not for amplifier purposes really. Okay, so these are the load lines. So we usually place the operating point somewhere below your VCC. Okay, so we have here your DC clamping of the input signal. So usually your input signal drives the emitter diode that is usually 0.7 volts. Okay, so the amplified current pulses drives the resonant tank circuit. So the input capacitor is part of a negative DC clamper. So the signal appearing across the emitter diode is negatively clamped. So it allows only the 0.7. So below 0.7 you don't have any output, but above 0.7 you have your output. So therefore making your output pulses less than 180%. So since this is in parallel with an emitter diode, your output voltage here once it is functioning is just equivalent to 0.7. Okay, so the problem with Class C amplifiers are harmonics. Okay, so harmonics are multiples of the input frequency equivalent to the group of sine waves with frequencies of 2FF, 2F3F, and so on. Okay, so your resonant tank circuit here has high impedance only at the fundamental frequency. So your fundamental frequency is your resonance frequency. So we don't have any efficiency formula for Class C amplifiers because technically we do not really measure the output or the input power for Class C amplifier. But what is important here, since this is a tuned Class C amplifier, this is usually used in a narrowband amplifier. So usually the formulas concerned here are the bandwidth, okay, which is F2 minus F1, or bandwidth related to the resonance frequency, and Q, which is the quality factor. Okay, so the bandwidth is inversely proportional with the quality factor. When your Q is high, that means you have a narrowband filter. Okay, because when your Q is high, your bandwidth is low. But when your bandwidth is high, that means you have a low quality factor or you have a wide band amplifier. Okay? So a large sinusoidal voltage at resonance with a rapid voltage drop above and below your resonance. Okay? So we have a current dip at resonance for a tuned Class C amplifier. Okay, so a tuned resonant tank, we to know that we are already tuned to a certain frequency, we're going to look for a decrease in the DC current supplied by the circuit. Okay, so measure the current IDC from the power supply while tuning the circuit. So you're going to tune the circuit here. At resonant frequency, your ammeter reading here will dip to a minimum value. So when this reaches a minimum value, that means the tank has the maximum impedance at that point, and that is your resonance frequency. Okay, so this is just how to solve for your XL. Okay, given this circuit. So at resonance, your XL cancels your XC. Therefore, your Q or your quality factor is just your XC, your RC, which is the parallel combination of your resistance in parallel. Okay, so this is the L and your C here. So therefore, you have here your RC divided by XL. So your quality factor has something to do with the inductive reactance and your resistance of your circuit. So since Class C has pulses, has something to do with pulses, we have here your duty cycle. Okay, so your duty cycle is equivalent to W all over T. Okay, so this is the width of your pulse versus the period. So when you say period, this is the start of your first pulse to the start of your second pulse. Okay, so the smaller the duty cycle, the narrower the pulses compared to the period. Typical Class C amplifier has small duty cycle. Okay, so the efficiency of a Class A amplifier increases as the duty cycle decreases. So you can see that the efficiency has something to do with your pulses. So since class A, they don't have pulses, they really have a very, very small, very, very low efficiency. Okay? So for the conduction angle, this is equivalent way to another way to state the duty cycle. Okay? So D is your angle here divided by 360 degrees. So this is in terms of time, okay, or in milliseconds, cycle time. So this is in terms of conduction angle. So for a conduction angle of 180 degrees, the average or DC collector current is IC sat divided by pi. Okay, so optimum stage efficiency varies with the conduction angle. So as the conduction angle decreases, the efficiency decreases. Therefore, the one which has the lowest efficiency is the one which has the highest conduction angle, which is your class A amplifier, which is conducting at the full 360 degrees. Okay, so for 180 degrees, that is your class B amplifier, your efficiency somewhat increased from 50% to 78.5%. And for a conduction angle below 180 degrees, which is your class C operation, it has the one which has the highest efficiency, which is 80% or higher. So therefore, optimum stage efficiency varies with your conduction angle. Okay, so that's it for our power amplifiers for our class A. So actually, class A, B is just a combination of your class A and B. So it is more on the higher efficiency side of class B. We just really wanted to eliminate your crossover distortion. So usually, the one which is being used in your amplifier circuit is class AB because it is somewhat the efficiency is lower than class B, but it eliminated the effect of your crossover distortion. And of course, class C, they are not really used for amplification but for tuned circuits, okay, in RF, usually in high frequency applications. Okay, so that's it for power amplifiers. Thank you for listening and watching, and don't forget to hit the like button after watching. Okay, thank you very much and God bless.